Hey everyone, before our last video unexpectedly came to an end, I was computing the limit of this function as x approached 2. Plugging in didn't work, canceling a factor in top and bottom didn't work, so we went to step 3, compute the one-sided limits. We computed the one-sided limit as x approaches 2 from the left, and then our video ended. Sorry about that. Now we're going to pick up where we left off and compute the one-sided limit as x approaches 2 from the right. And again, I'm going to factor the denominator. I don't have any plans to cancel in top and bottom, but when I'm computing my one-sided limits after I get division by 0, I find it helpful to factor the denominator. Okay. As x gets arbitrarily close to 2, x cubed is going to be very close to 8. So x cubed plus 4 will be 12 for all practical purposes. So for all practical purposes, the numerator is 12. We may be half a molecule short or half a molecule over, but nobody's going to know the difference. Now, as x approaches 2, x minus 2 goes to 0, but it never gets there because x never actually becomes equal to 2. But this is going to get close to 2, and it's going to approach 2 and get close. This is going to approach 0, and it's going to get closer and closer to 0 without ever actually becoming equal to 0. So we put an epsilon here for each one of these guys. Now the question is, as x approaches 2 from the right, does this factor approach 0 through positive values or negative values? If x approaches 2 from the right, is x bigger than 2 or less than 2? Well, if x approaches 2 from the right, then x lies to the right of 2 on the number line. And so x is going to be greater than 2. But we don't really want to know about x. We want to know about x minus 2. So we convert this inequality into an inequality that tells us about x minus 2. And we do that by subtracting 2 from both sides. So we get x minus 2 is greater than 0. And that tells us everything that we need to know. X minus 2 is positive as x approaches 2 from the right. So these two factors are both going to go to 0 through positive values. So this factor and this factor will represent with a plus epsilon. And we have 12 over positive times positive is positive. Epsilon times epsilon is epsilon squared. So we have positive divided by positive is positive. Big number divided by something going to 0, that's going to be infinite. Now, what do we make of all of this? it's helpful for us to remember what our goal was in the first place. We were trying to compute, quote, the limit of this function as x approaches 2 from either direction. And we end up having to do that by computing the one-sided limits. Okay. Well, we computed the one-sided limits. What is significant about our results here? What's the connection between one-sided limits and this thing that we call, quote, the limit, end quote? If the two one-sided limits are equal, which they are here, then the limit exists and it equals the same value as the two one-sided limits. So let's write that down. The two one-sided, the two one-sided limits are equal, so the limit exists. And now we'll encapsulate our results in a box. Now, how would we interpret our result? The limit as x approaches 2 of this function equals plus infinity. What that means is that as x approaches 2 from either direction, this function becomes large without bound in the positive direction. Now, maybe I could just sketch a graph of f of x. This is not part of the exercise that we just did. I'll tell you what, let's make that a whole nother exercise. Now here's the result of the previous exercise. This is the result, and here's what it means. That's what our result means. Now, let's draw a picture of that. F of x equals x cubed plus 4 over x squared minus 4x plus 4. Here's the line x equal 2. It's a vertical line. And our limit tells us that as x approaches 2 from either direction, f of x, the y value, is going to become large without bound in the positive direction. So y is going to go to infinity. So here's x approaching 2 from the left. And as it does, y goes to infinity. It gets large without bound. The net effect of both of these things happening simultaneously is that as x approaches 2 from the left, the graph goes up and toward the right. So that red piece is one part of the graph. Now, what about as x approaches 2 from the right? Same thing. As x approaches 2 from the right, f of x, the y value, still becomes large without bound in the positive direction. So as x approaches 2 from the right, y is going to go straight up like that. And the net effect of both of those things happening simultaneously is that as x approaches 2 from the right, we go from right to left and upward. And the red markings are what the graph of f of x looks like. So if I take off my training wheels now and just draw the graph of f of x, this is what it looks like. As we move along the graph in such a way that x approaches 2 from the left, f of x, the y value, goes to infinity. As we move along the graph in such a way that x approaches 2 from the right, f of x, the y value, again goes to positive infinity. So this is a graphic depiction of the information that's contained in the limit of the previous exercise. Now, I'm going to talk about a different kind of limit. I'm going to talk about what happens as x goes to infinity, or as x goes to negative infinity. And we'll consider some numerical examples. Here's our motivating example. We're working with the function f of x equals x squared. And we're going to compare values of x and x squared. So, let's say that x equals 1. Then x squared equals 1. And we could say that x squared is 1 times larger than x. They're the same size. Now suppose that x is 10. X squared is going to be what? 100? And so x squared is how many times larger than 10? 10 times, right? So x squared is 10 times larger than x. Now let's make x 100. If x is 100, x squared, let's see, 100 is 10 squared. So 100 squared is going to be 10 squared, or 10 to the fourth. So I guess that's going to be 10,000. So x is 100, x squared is 10,000, and x squared is 100 times larger than x. Let's make x 1,000. And I guess to do this, we're going to have to use scientific notation. X is 1,000, or 10 cubed. So x squared is going to be 10 cubed squared, or 10 to the sixth. So that's going to be 1,000,000. If x is 1,000, x squared is 1,000,000. And x squared is going to be 1,000 times larger than x. Okay, 1,000,000. We're going to make x equal to 1,000,000. Now I really have to use scientific notation. This is 10 to the sixth. X is 10 to the sixth. So x squared is going to be 10 to the 12th. And let's see, 10 to the ninth is a billion, 10 to the 12th is a trillion. So when x is 1,000,000, x squared is 1,000,000 times larger than x. Now let's look at our table and see what's going on here. As I move from top to bottom in this column, as I move from top to bottom, what is x doing? 1, 10, 100, 1,000, 1,000,000. X is getting large without bound, isn't it? So x is going to infinity. Now, as x goes to plus infinity, what's x squared doing? Well, x squared is getting large without bound also, isn't it? So right here, I'm going to write x is going to plus infinity. So x is going to infinity. X squared is going to infinity. They're both going to infinity. And yet, as x goes to infinity, x squared is becoming infinitely larger than x. Now that's strange. X is going to infinity, and of course x squared is going to infinity. But as x and x squared both go to infinity, x squared is becoming infinitely larger than x. That's amazing. Let's write that down. As x goes to infinity, x squared becomes infinitely larger than x. That's a heavy thought. Now, there's also another way that we can look at this. And maybe it's a good thing that we're doing this particular course online, because when we do this in the classroom live, in years of late, I haven't been getting the love from the students that I used to get years ago. And see, I ask my students, if I asked you for $1 million, would you give it to me? And you'd be surprised how many of them immediately say, no. Well, that hurts me. That really hurts me. And then some of them say, well, I don't know, maybe if you really needed it, and maybe if I had more than $1 million, I'd give it to you. That doesn't make me feel too much better. And then there's always some wise guy that says something like, well, if I had several million, maybe I'd give you $1 million. And then there's always one sweetheart in the room that says, hey, even if $1 million is all I had, Dr. Rossi, I'd give it to you. And I tell everybody to look at this student because I want them to know what an A student looks like. Now, what about this? All joking aside, if I asked for $1 million, would you give it to me? I don't know. Okay, let me describe the problem in a little more detail. Suppose that you had $1 trillion and I asked you for $1 million. Would you give it to me? Now, maybe the answer is yes. Remember, a trillion is 1 million times larger than a million. A trillion is 1 million 1 millions. So let's suppose that each of you had $1 million. And every day for the rest of your life, even if you live to be 100 years old, let's say that every day for the rest of your lives, you gave away $1 million. And we're neglecting any interest that the principal may accrue. Let's just forget about interest. If you had $1 trillion, and every day of your life until you reached the age of 100, you gave away $1 million. You know what? When you turned 100, you'd still have most of that $1 trillion. That's how much larger than $1 million $1 trillion is. $1 trillion is 1 million times greater than a million. Let's make another comparison. You have $1 million in the bank, and $1 comes up missing. Do you care? No. What's $1 compared to $1 million? Well, $1 million is 1 million times greater than $1. If we lose $1, we don't care. Well, $1 trillion is 1 million times greater than $1 million. If we lost $1 million, we wouldn't care. And that illustrates this paradox. X and x squared are both going to infinity, but as they do, x squared becomes infinitely larger than x. And the other way that we can look at it is x and x squared go to infinity. X, let's say it's 1 million, x becomes insignificant compared to x squared. See, when x is 1,000,000, if we threw that million away, would we care? No, x squared is 1,000,000,000. What's 1,000,000 compared to 1,000,000,000? A drop in the bucket, if that. So in addition to noting that as x goes to infinity, x squared becomes infinitely larger than x, it's also true that as x approaches infinity, x becomes insignificant compared to x squared. This is an important realization. Definitely an important realization. Now, I can generalize this, and I'm going to do that right now. And we'll say that n is the larger of the two. Now, we could also say that as x goes to plus infinity, x to the m, the smaller exponent, becomes insignificant compared to x to the n. Now, what happens if x is not going to positive infinity, but instead x is going to negative infinity? The same thing. Magnitude-wise, x to the higher power becomes infinitely larger, magnitude-wise, than x to the smaller power. M and N are still positive whole numbers, and N is the larger positive number. If X goes to negative infinity, the same thing happens. X to the power of the larger number becomes infinitely larger magnitude-wise than X raised to the smaller number. Or to put it another way, X to the smaller power becomes insignificant compared to X to the larger power. And people may wonder about this and say, well, let's let N equal 3 and M equal 2. And let's say that X is negative 1 million. Then X to the M is negative 1 million squared, which is a trillion, positive a trillion. And X to the N is negative 1 million cubed, which is negative 10 to the 18th, negative quintillion. Well, suppose in my bank account I had $1 trillion, positive $1 trillion in my bank account. But suppose that my debts and liabilities were negative 1 quintillion, negative 10 to the power of 18. So this number, my liabilities, are negative 1 million times my assets. Am I going to say, oh, okay, I'm fine. I've got $1 trillion of assets, and I have a million times $1 trillion in liabilities. The fact that this is negative is not going to keep this from wiping out my assets, is it? To look at smaller numbers, let's say that I have $100,000 of assets and $1 million of liabilities. So my assets are positive 100,000, my liabilities are negative 1 million. Am I going to say, oh, 100,000 is greater than negative 1 million because negative 1 million is negative? So I'm all set. My assets are greater than my liabilities. Am I going to say that? I'm not. If this is positive 100,000 and this is negative 1 million, I'm in big trouble. So the fact of the matter is as x approaches negative infinity, x to the larger power becomes infinitely larger magnitude-wise than x to the smaller power. And as x goes to negative infinity, x to the smaller power becomes insignificant compared to x to the larger power. Now, why am I talking philosophically like this? Because we're about to apply this to limits. Yep, it really does have applications, and we're about to see that. We're going to see some examples. Here's a nice example. We're computing the limit of the quotient of two polynomials as x goes to positive infinity. And here's how we do that. We look at the numerator and we say to ourselves, as x goes to infinity, how does 6x squared compare to 5x to the fourth? And we say as x goes to infinity, 6x squared is insignificant compared to 5x to the fourth. And as x goes to infinity, negative 2x is insignificant compared to 5x to the fourth. So as x goes to infinity, the numerator looks like 5x to the fourth, the term of highest degree. Now, what about the denominator? As x goes to infinity, 5x is insignificant compared to x to the fifth, and 1 is insignificant compared to x to the fifth. So as x goes to infinity, the denominator looks like x to the fifth. So as x goes to infinity, this is really what our function looks like. And I can simplify that algebraically. I can divide top and bottom by x to the fourth. Okay, as x goes to infinity, what does this look like? We're dividing 5 by something that's infinitely large. So we have a little number, we're dividing it by a big number. If I have 5 pizzas and I have to cut them up in enough pieces to share with 1 million people, how big a piece is each one going to get? Each person's going to get a tiny, tiny, tiny piece. If I divide 5 by 1 million, I get a tiny number. And as x goes to infinity, that tiny number gets smaller and smaller. So, little number divided by big number, that goes to 0. Well, that was pretty easy. I think what we need to do now before we do any more examples is write down exactly what we learned from all of this. Yeah, lesser degree, that's fine, but maybe I should just say lower degree. What did we do in the last exercise? We looked at all of the terms in the numerator and said, these terms of lower degree, they're insignificant compared to the term of higher degree, so we threw them all away. The only term we kept in the numerator was the term of highest degree. And then we did the same thing in the denominator. We looked at the terms of lower degree in the denominator and said, these terms are insignificant compared to the term of highest degree in the denominator. So we threw all the terms of lower degree in the denominator away. And we ended up computing the limit of the quotient of one term in the numerator and one term in the denominator. Now, part 3 is very important. This trick for computing limits only works if x is approaching plus infinity or x approaches negative infinity. So if we're computing the limit as x approaches 2, don't go throwing away the terms of lower degree. It's not going to work. This trick of throwing away the terms of lower degree only works if we're computing the limit as x approaches plus infinity or x approaches negative infinity. Now, let's do another example. We're computing the limit of polynomials as x goes to negative infinity. So what are we going to do? We're going to take all the terms of lower degree in the numerator and throw them away. And we're just going to keep the term of highest degree. We're going to take the terms of lower degree in the denominator and throw them away. We're just going to keep the term of highest degree. And now we can simplify. We divide top and bottom by x cubed. So we have 6x squared over 5. Now I guess we're going to have to get philosophical. As x goes to negative infinity, x is negative and it's getting large without bound. So if x is negative and we square it, it's going to be positive, isn't it? And if we take something that's large without bound and square it, we're going to get something that's large without bound. So a negative squared is positive. Something that gets large without bound continues to get large without bound if we square it. So x squared is going to positive infinity. And if we multiply something that's going to positive infinity by 6, it's still going to go to positive infinity, isn't it? And if we take the numerator, which is going to positive infinity, it's getting infinitely large in the positive direction, and we divide it by 5, it's still going to be positive, and it's still going to be going to infinity. Something that's infinitely large or large without bound is still going to be large without bound when we divide it by 5. So this is going to go to plus infinity. Okay. Now the bad news is, I guess that completes our lecture for today. The good news is, we've done just enough to allow us to be able to do some homework, and the homework will be forthcoming.